So this is POW problem of the week number 12. For this one, they are giving us a shaft which is similar to the design problem from prison problem of the week number 10. Um, and they want us to design suitable bearings to support the load for at least 7 times 10 to the 7 cycles at 1500 RPM. The dimensions are all in imperial units, and they want us to use a hydrodynamically lubricated bronze sleeve bearing with an ON value equal to 20, a length over diameter equal to 1.25, and a clearance ratio of 0.0015. They want us to find all the three torques being no load, stationary, and rotating, and they also want us to find the power loss for each bearing from each bearing. So the values are given in this table for both the distances and force initially applied. First thing we want to do is create a free body diagram to find the reactionary forces. As you can see here, we have um, both reaction forces found. R1 is equal to seven 1,750 pounds, and then R1 is equal to negative 1,250 pounds. Next, we want to find the max moment, which is 5,000 pounds per inch. Then we find the diameter, which since we were given the ratio from length over diameter and the the length of the shaft, we can find diameter to be 9.6 inches. Next, we need to find the experimental eccentricity ratio, which is this equation right here. The only thing you need to plug in is your ON value that you were given here, and I get a value of 0.747. Then we determine the tangential velocity right here. You want to plug in your RPM as well as the diameter to then find the tangential velocity, which I got 753.6 inches times revolutions per second. Then we need to find the Ökvirk dimensionless parameter, which you can just use since it's below length over diameter ratio of 4, you can just use this equation right here, which you can get a value of 1.59 when you plug in the ON value. Next, uh, we need to find the bearing parameters. So you need to find CD first, which you can do by multiplying the clearance ratio, which we are given in the problem, times the diameter, um, which I was able to find as 0.0144 inches. And then you divide that by 2 to find CR, which is 0.0072 inches. Now from here, since we aren't given the type of oil or lubricant given, we can still solve for it using this equation right here, which I derived from this equation for force, and you can solve for the absolute viscosity, which I was able to get as 0.0312 microreynolds, and this is for the first reactionary force, R1. I do this again for R2, which I get as 0.0438 microreynolds. I'm going to convert this back into normal Reynolds just because it'll be easier to keep everything more simplified when multiplying the absolute viscosities with everything else to find the torques. So, afterwards, we need to find the no load torque bearing for one as well as for the second reactionary force. Here is the equation to solve for it, and once you do, uh, I was able to get a no load torque of 5.68 pounds per inch, and then for the second I was reactionary force, I was able to get it for 7.97 pounds per inch. And even though it shows here that it's in micro Reynolds, I converted it to Reynolds for the rest of the problem's sake. Next, we need to define the stationary load, which essentially is the no load torque equation, except we need to include this second component. So I replugged in the no load torque values into the equation, and multiplied it by we need to by the eccentricity ratio right here, and we were able to get a value of 111.37 pounds per inch for the reactionary first one, and then for the second one, we were able to find it to be 156.3 pounds per inch. Lastly, or thirdly, we need to find the rotating torque. And for this one, we need to first find the angle phi, which is the same for both our reactionary forces. Um, and how we do that is by using this equation right here. Uh, you just plug in the eccentricity ratios that we had originally found, and we got an angle of 34.95. Then we need to plug in our stationary torques times the forces from each reactionary force, and then multiply by CR and sine of the angle that we found, and we are able to find that our rotating torques is 118.6 pounds per inch and 163.5 pounds per inch for each respective bearing. Lastly, we need to find the power loss in each bearing. So for that, we use these two equations right here where we plug in the rotating torques and as well as the revolutions per second for each one. Um, and once we're able to do that, you can get a value of 1,000 or 18,627.8 pounds per inch over second, which is units of power, and 25,682.5 pounds per inch over second for the second bearing. And then I took the liberty of converting this to horsepower, so it's a easier unit to reference. So 34.3 horsepower, as well as 47.343 horsepower for the second bearing. And then after that, you should be good to go now that you're able to solve everything. Take care, guys, and have a good one.